Hello and welcome to this presentation describing the STM32H5 product lifecycle. The product lifecycle allows to control access to different assets, code and data of the product, including during development, manufacturing and after sales. It allows to provision the product with different distribution models, taking care of the code and data provisioned. This presentation is part of a set of presentations that describe the security mechanisms offered by the STM32H5 and related secure firmware. The goal of this presentation is to provide some details on the usage of the product state, including the multi-OEM provisioning aspect and the debug authentication control. The following topics are going to be explained. First, the multi-OEM model that enables firmware images coming from different OEMs to be installed securely. Second, the various states of the lifecycle will be described. At last, debug authentication according to the current product state will be explained, particularly in case of field return. The following images have to be provisioned: the immutable root of trust, or IROT, the secure image containing secure kernel and applications, and the non-secure image containing non-secure kernel and applications. These images can be provided by independent OEMs. Either one OEM provides the three images, or one OEM provides the IROT and secure image while another one provides the non-secure image, or one OEM provides the IROT while another one provides the secure and non-secure images, or one OEM provides the IROT, another one the secure image, and a last one the non-secure image. The product lifecycle is designed to support this model based on up to 3 OEMs. A typical product configuration taking benefit of trust zone is shown on the figure. The relationship between this model, based on up to 3 OEMs, and product lifecycle is explained on this slide. Once IROT is provisioned, the product lifecycle becomes the IROT provisioned state. Once IROT plus secure image are provisioned, the product lifecycle transitions to trust zone closed or TZ closed state. Once IROT plus secure image plus non-secure images are provisioned, the product lifecycle becomes either the closed or locked state. This state machine supports backwards transitions only in case of field return, as explained in the following slides. When several OEMs contribute to install all images, a sequence of installs is required, starting with IROT provisioning. The last installed firmware oversees new firmware and keys to install. A typical MCU device lifecycle is based on 3 separate installs. For each step, the STM32H5 proposes secure lifecycle management mechanisms embedded in the hardware. First, the immutable root of trust, or IROT firmware, is programmed. Second, the secure operating system and secure applications are programmed. Third, the non-secure operating system and applications are programmed. The installs are chained. IROT offers services to program the secure image and keys, and the secure OS offers services to program the non-secure image and keys. Debug permissions are also reduced all along the sequence. When IROT performs the handover to the secure OS, it also restricts the debug permissions to HDPL2 and non-secure. When secure OS performs the handover to the non-secure OS, it also restricts the debug permissions to HDPL3 non-secure. In this example, a first OEM provides both IROT and secure image, and a second OEM provides the non-secure image. Once IROT and secure image are installed, the first OEM transitions the lifecycle to TZ closed state. Thus, the non-secure image has no visibility on what happened before it's launched. In this example, a first OEM provides the IROT, a second OEM provides the secure image, and a third OEM provides the non-secure image. Once IROT is installed, the first OEM transitions the lifecycle to IROT provisioned state. Once the secure image is installed, the second OEM transitions the lifecycle to TZ closed state. This slide introduces the lifecycle state diagram assuming that trust zone is enabled. It's simplified because it doesn't include the field return additional states. This is an overview. Each state will be detailed in the next slides. The list of product states from top to bottom is Open, default state when no firmware is installed, Provisioning, IROT provisioned, TZ closed, Closed, Locked. The supported transitions can be requested through the debug interface or via the system bootloader. This slide details the features of the open state. It allows to develop the product as it allows the debug of the code in both secure and non-secure states. Both addresses must target a secure area when trust zone is enabled. Using boot pin and unique boot entry or UBE allows to launch user flash code through STIROT. In this open state, hide protect level and trust zone isolations are available. They enable to protect data according to current HDPL and secure states. Since the root hardware unique key or RHUK is not activated, provisioning in this state will not be valid for others. The provisioning state allows to manage the provisioning of the product, partial or full. The microcontroller is provisioned with ST security services in system flash, but can be configured to let the full control of the boot chain to OEMs. Security services are provisioned by ST in system flash, which is immutable. They provide the root of trust of the platform managing the verification and the update of the first updatable code or UROT. The root hardware unique key or RHUK is programmed in this state. Debug authentication is natively supported by STM32H5 platform. It means that the data used by ST debug authentication or STDA must be provisioned at a defined location in option byte keys. The debug authentication configuration must be done only when the product state is provisioning. It cannot be performed when product state is open. The product state becomes IROT provisioned when it's assumed that immutable root of trust is installed, including its configuration, code, option bytes, secure storage. This state is relevant when a first OEM provisions the IROT and another one provisions the secure and possibly non-secure images. The IROT allows the update of the image containing both the secure and non-secure images. It can launch the bootloader if the next level is not OK. The embedded bootloader is located in the system memory, programmed by ST during production. It's used to reprogram the flash memory by using USART, I2C, I3C, SPI, FD-CAN or USB-FS in device mode through the device firmware upgrade or DFU. The debug authentication protocol can be launched in IROT provisioned product state. The protocol is based on initial message, posted by the host combined with a reset to launch the debug authentication process on the device. Challenge message, the device generates a random value to be signed by the host when sending back the response. And response, the host sends a message to the device proving its authenticity. This is done using a tool to generate a token. The product state becomes TZ closed when it's assumed that the secure OS is installed in trust zone. Debug is opened for non-secure applications. All peripherals and memories mapped as secure during secure boot cannot be dumped, debugged, or traced. The UROT must allow the update of the non-secure image. It can launch the bootloader if the next level is not OK. The product state becomes closed when it's assumed that the product configuration is finalized. No debug is possible except through debug authentication when field return is enabled. Progressing to more closed state is the normal product lifecycle that doesn't require security measures. Transition in direction to open state is a regression controlled by the debug authentication control. See explanations hereafter in the presentation. If debug unlock policy is set to locked, no regression is accepted. Debug authentication is fully deactivated in locked state. It means neither regression nor debug opening are possible. In this figure, all states are represented, including the ones associated with field return. ST debug authentication manages the debug authentication control feature, allowing to control the debug reopening and regressions of the product for after sales of it. Field return is possible only if debug authentication configuration has been performed in the provisioning state. This configuration includes the SHA-256 of the root certificate public key, SOC permissions that define the allowed regressions, full or non-secure, and the maximum allowed intrusive debugs for secure and non-secure states. The debug authentication control is ensured thanks to a protocol based on ARM PSA ADAC specification. Platform Security Architecture, or PSA, is a security certification scheme for Internet of Things hardware, software, and devices. The Authenticated Debug Access Control, or ADAC specification, defines the protocol that allows a target to securely authenticate a debug host. This debug authentication state allows controlling that the host has a trusted certificate with permissions. Permissions definition allow a lot of flexibility. In the default model, ST considers full or partial regression or to open the debug for non-secure. The protocol implements a challenge response mechanism based on asymmetric cryptography to authenticate the host. It relies on a key pair with a public key stored in the device and a private key from the host library used to sign a random value generated by the device. The protocol implements a bidirectional communication between the host and the device through a mailbox interface located in the DBG MCU. NS regression is a temporary state initiated by the debug authentication system in transition to TZ closed. The epoch NS counter is incremented. This transition opens the device to authorize the debug of the non-secure application software without compromising the security of the ROT functions. Note that the option byte key related to HDPL3NS and all user flash non-secure sectors are erased. The starting state is closed. The debug tools are used to authenticate debug regression access rights with the debug authentication library running on the device in the HDPL1. After verifying the credentials, they put the device into intermediate state NS regression. From this state, the device regresses securely in HDPL0 to TZ closed. If the implementation uses some sectors in eData to allow erasing their state is changed to no eData, erase is done, then reconfigured to eData. As we're not able to distinguish secure from non-secure eData sectors, the erase is done whether the sector is insecure or not. Regression is a temporal state but non-volatile to manage the full regression to open state, removing all user flash code and data, including insecure storage, from HDPL1 to HDPL3. This transition is a full regression. The epoch NS and epoch S counters are incremented. Note that the option byte key address ranges related to HDPL1 to HDPL3 and all user flash sectors are erased. The starting state is any except open and locked. The debug tools are used to authenticate debug regression access rights with the debug authentication library running on the device in HDPL1. After verifying the credentials, it puts the device into intermediate regression state. From this state, the device regresses securely in HDPL0 to open. Debug constraint is a temporal state until power on reset to manage debug based on the permissions acquired by the debug authentication protocol. The product state is not changed. Debug is reopened for the requested HDPL and security states. Access to debug can therefore compromise the platform security. This can be limited by restricting the debug access to HDPL3 non-secure. When trust zone is disabled, the state TZ closed doesn't exist and the debug authentication is based on a password authentication method. Only the hash of the password has to be provisioned. This state allows to execute the STDA embedding the ARM PSA ADAC protocol through JTAG or SWD with a host. The only permitted action is to launch a full regression. When trust zone is disabled, the full regression is done to open state after successful verification of the password. The epoch NS counter is incremented. All option byte keys from HDPL1 to HDPL3 are erased, as well as the complete user flash. Thanks for having attended this presentation. You can also refer to the following presentations: Security Overview, Secure Data Storage, and Debug Authentication.